Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is the fourth in a series on the fundamental theorem of calculus. The first one was actually an introduction to the integral function. The second was the concept, theorem, and proof of the fundamental theorem of calculus part 1. The third video was using that fundamental theorem of calculus part 1, and this video is introducing the most important, the heavy hitter, the fundamental theorem of calculus part 2, which is also known as the FTC2. I didn't write that for the fundamental theorem of calculus part 1, but this is FTC2, and fundamental theorem of calculus part 1 is also known as FTC1. To do this, I want to motivate the fundamental theorem of calculus part 2 before we go into the theorem and the proof. The motivation is king here. It's so awesome. So let's see, we have a position function, s of t. It just describes the position of a particle, okay, with respect to time. So the particle might be 5 feet ahead or whatever, right? Then if that's the case, we know from differentials that ds, the differential of s, is just the derivative of s times dt. Let me say that again. We have in previous parts of your calculus course encountered that if y is equal to a function of s, then the differential y is equal to f prime of x dx. Well, in this case, we have not y as a function of s, but s is just s of t. You could say y is s of t, but most of us would just say s is s of t. Okay, so s is equal to some function of time, which tells us that ds is s prime of t times dt, just by using the same exact logic. Of course, s prime is the rate of change of position with respect to time, which is a velocity function. And that's why I say ds is v of t dt, because change, the derivative of position is velocity. So I hope you're up to speed with that. Now, suppose we want to sum up all these little itty bitty changes, because that's what ds is. ds is just a little change in position. I should probably illustrate that. You have this particle. Here it is on this paper. And it moves a little bit. Let's say it just moves over to here. And it's at this position at a plus a little wiggle, right? And then maybe it moves this much more at a little bit of time later, maybe a plus 2 wiggles or something like that, right? And maybe it moves backwards, right? So this would be s of a plus 3 wiggles. So in other words, every time that we increase time, the particle can just change positions. It can move back and forth and move back and forth and move back and forth, or it could just continually go forward. We don't know. Nobody told us, right? In the end, after a bunch of infinite little changes like that, it lands at wherever it wants to land at the end of its time, okay? So it doesn't really matter, but after a bunch of little movements and we stop time, we say, okay, you're done moving. It's sort of like you walk in a room and somebody says, okay, everybody take a step in a random direction. So people do. You say, stop. Okay, now everybody take another step in a random direction. Everybody does. Stop. And you do that for an hour. And then at the end of the hour, you say, okay, mark your ending position. So you mark your ending position and you had marked your initial position. Okay, that's the idea of this example, is that you have an initial position and an end position. Between those two times, you did a lot of stepping back and forth, okay? And those little steps are called wiggles in position, DS's. So I hope you understand that that really is what a differential is. It's just a change in that variable, and that variable stands for position. So we just have this minor change in position. So the question is, suppose we want to sum up all these changes, all these little steps over a time interval from A to B. Again, you started at step right here at time A. You did maybe a step forward, 5 steps back, that type of thing. You wiggled back and forth, so on and so forth, so on and so forth, so on and so forth. But then when I call time, you were right here. And I say, I want to know what is honestly the difference between your beginning and ending time. What is the difference in your position? If you were to sum up all of those changes, well, the first step was a forward step. Let's just say. So that's a forward step, and your next step was a forward step. The next step erased all of those steps and basically said, you know what, we've only moved that far. So a forward step and a backward step of the same size will erase each other. Okay. And really, in the end, all that really matters is your change in position. So if you sum up all those step forwards and step backs and stuff like that, the infinite sum of all those movements will just be the difference between your ending position and your beginning position. That's it. Let me illustrate this slightly differently because I really want to drive this point home. And if you get it, just click fast forward and fast forward a couple steps, okay? But it's sort of like this. Here I start. That's my position, time A. And I'll step forward, step forward, step forward, whoops, step back, nope, step forward, step back, step forward, step forward, step forward, step back, step back, step back. In the end, really, all we've done is taken a single step forward. Even though we've actually done all this movement, the truth is we've only taken a single step forward by the time is called. So if this is our final position, in the big scheme of things, we've only moved one step away. Now the second part, how would we write this as an infinite summation? How would you write this infinite summation, basically? Well, I would go ahead and start with, what if we were to add these up, right? So I'm going to say, let's go ahead and add up all of our steps. Let's say we took n steps. So I'm going to add from 1 to n all of our little steps. Well, our steps were all these little steps sizes ds's, right? Those were our steps. So I took a little step forward, took a little step back, that type of thing. But we know what ds equals. We have it written up above right here in black ink. ds is equal to v of t dt. So, okay, this is just going to be the sum, I equals 1 to n, of v of t dt. But really, v of t is s prime of t. Again, that's just from this right here. Velocity is just derivative of position. So we could say, well, that's the sum, I equals 1 to n, of s prime of t dt. But interestingly enough, I said this infinite summation. So I'm not taking n steps, I'm taking an infinite number of steps. So let me go ahead and adjust that notation slightly and say, oh, whoops. Let n go to infinity. We want an infinite number of steps. So let's take that limit as n goes to infinity of that summation, I equals 1 to n of s prime of t dt. That is a Riemann sum, and we're taking the limit of that Riemann sum, and we know that we have a notation for it called a definite integral. We are taking the sum of all of our steps starting at time A and ending at time B. Let me highlight that because I'm looking at it. Starting at time A, ending at time B. So I'm going to sum up all my steps from time A to time B of this function dt. Well, oh, by the way, I had a little dt there. It should be a delta t. It's not that big of a deal. So that is how you would write that infinite sum. Okay. That is the same thing as part A. That infinite number of steps, the net result is that it's just s of b minus s of a. And another way we could have written that is as an integral. That is, since a and b are the same ideas, you're just saying, hey, what if I were to step forward and step back and step forward and back and forward and back? What's the end result? It's just s of b minus s of a, your position at the end minus your position at the beginning. Well, another way to have written that is I'm going to add up all my steps. And I end up with this, which is this. And so S of B minus S of A, which was the answer to part A, it must be the same thing as the integral from A to B of S prime of t dt. And by the way, folks, that is the fundamental theorem of calculus, part 2. Let f be continuous on the closed interval from A to B, and let capital F be the antiderivative of little f, or be an antiderivative of little f. Then you can easily evaluate the definite integral from A to B of f of x dx by evaluating its antiderivative at B minus its antiderivative at A. Let me bring it back to that example we just did. I hope you would agree the thing I took the derivative of to arrive at this is S. So the integral, the definite integral of S prime from A to B is the antiderivative of S prime, which is S, evaluated at B, minus the antiderivative of S prime, which is S, evaluated at the lower limit A. I also want to draw your attention to the fact that this notation, f of B minus f of A, mimics my notation for the derivative, right? So if I took the derivative of an integral, it would be f evaluated at the top times the derivative at the top minus f evaluated at the bottom times the derivative at the bottom. Now I'm saying if you want to take the integral, if you want to take the integral from A to B of the derivative with respect to x of some function, that will be that function evaluated at the top minus that function evaluated at the bottom. So the fundamental theorem of calculus part 1 says derivatives sort of undo integrals, and the fundamental theorem of calculus part 2 says, oh, by the way, integrals sort of undo derivatives. They sort of undo each other. Pretty rad. Now let's go ahead and prove this bad boy, and we'll use it in a different video. All right, and there's no alternative form of this, by the way. This is just the only version of it you need, and you're going to use it for the rest of calculus. Literally every single time you touch calculus from this point forward, you're going to be using the fundamental theorem of calculus part 2. We start the proof by just stating what they allow us to state. Let f be a continuous function on the closed interval from A to B, and assume that capital F is an antiderivative of little f. That is, the derivative of capital F is little f. Now I'm going to bring into play something that we need that is not mentioned in the antecedent of this theorem. We're going to let g of x be the integral function of f. So the integral from A to x of f of t dt. And this is really why the fundamental theorem of calculus part 1 precedes the fundamental theorem of calculus part 2, is you need it to prove the fundamental theorem of calculus part 2. If g of x is equal to this integral function, then by the fundamental theorem of calculus part 1, g prime of x is equal to f of x. Okay, that's the fundamental theorem of calculus part 1. There's no escaping that. We've actually proved that. So this implies that g is an antiderivative of f. Okay. And again, we're going to pull in a theorem that we've introduced in the past. Since g prime is equal to little f and capital F prime is equal to little f, then f and g must differ only by a constant. So capital F, that is, capital F of x must equal g of x plus some constant c. It's kind of important that I state that we're working only on the interval from A to B here. So I should say for x between A and B. Now it's time to go to work and actually prove the theorem. We're going to start with f of b minus f of a. So capital F of b minus capital F evaluated at a. I'm doing this because I want to prove that that difference is going to be the integral from a to b f of x dx. So capital F evaluated at b, let's see. that's going to be the same thing as, according to this equation here, the g of b plus that constant c minus the quantity g at a, again, plus that constant c. Well, you can see the constants will disappear, and we have g of b minus g at a. And you think, man, there's nothing I can do here because I'm stuck. I don't even know what that function g is. Well, you sort of know what that function g is. That function g is the integral function here. And note that if I were to evaluate g at a, I'd take the integral from a to a. Let me say that down below. I'll say, but g of a is the integral from a to a of f of t dt. And since that is an integral from a to a, in other words, it goes nowhere, you have no area. Thus, f of b minus f evaluated at a must just be g of b. But remember, g is the integral function starting at a and going to whatever I'm plugging in, which is b in this case. And there you have it. That has now been proven. F of b minus f of a is equal to the integral from a to b of f of t dt. Yay! QED. We are totally done with this proof. And now we're really past the hardest part, I think, in the initial integral chapters. Once you get past the fundamental theorem of calculus parts 1 and 2 and start using them, it's all downhill from here. All beautiful, fun stuff. So let's go ahead and stop the video now. And in the next video, we're going to use this stuff until you just vomit integrals. Well, no, I don't want you to do that, but we're going to use this stuff a lot.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.